So last week we talked about building a simple thread pool, which we did using a standard queue, right, mutex and a condition variable to notify threads when some work is ready. And we can later work on this some more, improve it. But there are some things that could be improved here, mainly exception safety of this constructor. But you guys asked to show you how to build other multi-threading components, and I suggested a queue. So let's try to let's see if we can build a multi-threaded queue and later change this thread to this thread pool to use it. So I'm going to just comment this code out here. We'll use it later. And we'll start here. Okay, so queue. Thread safe consumer producer queue. So this means that a thread, one or multiple threads, can be trying to pop elements off of this queue, and they would block. Most likely, we want it to block if the queue is empty, and a producer or many producer threads can just go in and whenever they produce something, push those elements onto this queue. And at first, we will write an unbounded queue. That means a queue that can grow indefinitely. And later, if we have time, we can try to rework it into a bounded queue, meaning a queue that you can give maximum capacity to. And once you reach this capacity, if no consumer thread has popped something off of this queue, then the producer thread or threads would also be blocked. And they will be unable to push more elements onto it. So let's see, class, what are we going to call this one? Let's call it U Q for unbound. Constructor, what was it? No, I cannot see. Media keys or function keys on my keyboard. Let's see, function keys. Oh. Okay. So we're gonna probably need some sort of a constructor. Maybe a destructor. I'm not sure. And last time we used condition variable and a mutex to protect the thread pool and the queue that thread pool had internally. So let's see if we can do something similar here. So let's see, how did we declare these variables before? So queue pointer to a new work item. Okay. Queue log condition. All right. Let's start with this. With this. There. And this, of course, will be a template. Template on 519. I got a cat walking around here. Suddenly something happens like this. Don't mind. Okay. Work queue type. So we can reuse again the STL queue. Should be fine for our purpose. No need to define this work queue item like we did before. For the thread, there will be, well, there may be Sentinel defined here, but it will be defined externally. So this queue doesn't really need to worry about holding any special value that would allow it or allow the thread pool to shut down cleanly. Like last week with the thread pool, right? We had to put a special value to tell these threads that, okay, there is no more work. You can now exit. And as it turns out, I was actually mistakenly pushing unique pointers. Excuse me. I think it would have been okay to just push some sort of a functional like this, because that can also have a special value. If you create an instance of it without actually pointing it at a function pointer or at a lambda expression, then it will it will be testable. You can put it in if statement, like bang item, and it will tell you whether it had anything assigned to it or not. So maybe we can rework this later as well. Okay, and because it's a bounded or unbounded queue, but producer consumer multi-threaded, I think it's better. It would be an easier interface if the pop function just pops the element while blocking when there's nothing there. If you remember the SDL queue that we used for the thread pool, it lets you peek at the front element, and then as a separate call, it would pop this element off. And this was needed to provide certain exception safeties. So let's see if we can provide a similar exception safeties here while merging those two calls into one. Okay, but let's do a push first. So push, and we want to take a const key item. This will do something, and then signature of a pop. You can do t pop. There, simple. So let's see. First thing we likely need to do is just acquire the mutex, right? Because it's a shared data structure. So before we push anything on it, obviously it needs to be locked. So let's see. We have the queue lock mutex. Okay. So let's lock it and maybe do it in its own subscope. So we are going to lock this queue and then simply MQ push. And if you notice, there are two signatures to this function, so we should probably implement the same. So one signature takes a constant reference, the other one an R value reference. So the R value reference one can be more efficient because it wouldn't make copies, right? It would move. But let's start with the signature. So we're going to push item onto this queue, unblock, and then condition that notify one. So this notify one, right, is in case there is a thread blocked waiting on some item to show up on the queue. And why would it be waiting? Well, because it's empty and we just pushed one element, therefore we only need to notify one thread. Okay, so that is that. Nice and simple. Let's then write another version of push for the R value reference parameter. So it will be t ref, and let's see. Again, we take a lock. Now this push here, the queue. Let's look at the signature again. So that would be push. No, I missed it. Okay. Well, it takes a ref. So what we need to do is move it. And keep in mind, move is nothing more than a cast, but it needs to be, because of the way template parameters are deduced, you need to cast this item back to t ref, and that's exactly what move does here. Otherwise, it would lose this property of being an r-value reference, and I believe the other version of push would be called, basically defeating the purpose of writing this this push. So let's think about now exception safety here. We take a lock, that's fine. The only thing that can really throw an exception here is this push, in case it needs to allocate some memory, which it most likely would, possibly, depending on its underlying implementation. If this queue was implemented using a vector, then maybe it wouldn't. So if this throws, that's fine. We will exit this function, release the lock, and nobody will be notified because, well, we didn't successfully push on the queue, so that's okay. And this other push, yep, that looks fine also. Now pop. How do we want to pop? We definitely want to start with a lock, I would think. So let's see. Let's start with a lock. And here, in order to pop, we need to make a copy, right? Because we need to make a copy of this element, because this queue that we're using has a separate front end and pop methods. So let's do this. We're going to make a temporary copy, and we'll get it from mq that was front. However, like we did here, you can try to move it off the front of the copy. So let's try to move it if we can. If we can, it will use the move constructor of t. If it has one, we can test this later using some sort of a noisy type that will print what's happening, as in it will print which social member functions of it we're calling. Okay, so we have this, and then the queue needs to remain locked still. And now queue dot pop. Okay, and let's see what could possibly throw here. The only throwing operation, I believe, would be this move. Although you would hope that the move constructors, if they are there, would not be throwing. But if there is no move constructor, then this would be a copy constructor, even though we're using this move here. Then this copy could possibly throw. So what would be the state here? Right, the queue would still contain the element that it had in the front. So I think this would be okay. So let's do this again in its own subscope. This is all we need to lock the queue for, and then return again. Let's try to move temp out of this spot. That's right. It's defined over there. All right, so let's just do that. We'll see how this is going to work. There, so that should be the start. Simple enough, I think. Expected semicolon class. Yeah, I did put a semicolon. There we are, it builds. Okay, and as far as the constructors, destructors, we need to define anything. Well, let's see. I don't think we do, because the default constructor and destructor are fine here. We don't care if we're being destroyed while we still hold elements. So it shouldn't matter. That's not our problem. Let's see. the problem of the consumer to make sure that they're not destroying us with some elements on it. Now I wonder regarding this lock. Wait, I did the wrong thing here. No, of course. So I took the lock, but what if it was empty? Then we should block, right? So we need to repeat this condition variable while loop here. So we took this log. There we are. This is what we need to do, right? Take the log. Once we successfully take the log, then we need to check the condition. Right? And the condition is the queue actually empty or not? So again, we're using this predicate here to spin in a loop and wait until the queue is non-empty. But let's see. I wonder what should the destructor do? Should we, in a destructor, try to take the log, clear the queue, and then notify one because the thread is blocked somewhere else? We'll see. We'll test this out. So let's see, this looks okay now, I think. Take the log, enter the condition wait. Once we grab the log, because the queue was not empty, we move off of its front, pop, and return what we moved. Okay, I think this looks okay. So let's see if we can test it. Did I have a noisy type somewhere? I did. I have this, yeah, I have this T we can use. This instance of T will print that's being created, moved, and so on and so forth. So let's see if we can use that to see what's going on with the queue. Include T. Yeah. So first, let's try to U Q of T. I know this may be confusing because here T is the template parameter, but here in this header file, T is actually the name of the class. But in this case here, I'm instantiating the template with the actual type T. So there, let's call it Q. Just Q. Let's do Q push, and we're just going to create a T with 1. This T has many different constructors. So let's see. We should enter. Oh, excuse me for a second. I think it's Kitty. Hey, Blue. Come on, dude. I'm on air. All right. Let's see where we're gonna go. Build fail. What happened? Why? Undefined symbol UQ. Oh, that's right. I defined them, but didn't provide an implementation. So let's just say for now, default. And same for this guy. There. But for now, we'll use default constructor and destructor. Okay, so we entered because we're creating a temporary here in place, so it can treat it as a R value reference. So we entered into the proper push. Let's see, we take the log, move, and then the move. See, uses a move constructor again to move it onto the queue. That's good. Modify 1. Good. And then 2 T's were destroyed because there was 1 T that created this temporary here that was moved out of, and then a second T that was living on the queue. So the moment we started destroying queue, it called the destructor of this underlying queue, and that cleaned up whatever elements it had on it. Let's just rename it real quick. It's not a work, it's just a queue in this case. Okay, so now let's test this case. Well, let's try to see if we can test pop. So let's do cout q.pop. And we can do that because this T that I'm using here has a stream output operator defined somewhere. There we are. So we can print instances of it. All right, so this and this here. No, build failed again. Of course. And look. Okay, now we're in the pop. Take a log. Check that the queue is not empty. Move again. So see, this is good. We're moving the element off of the queue instead of copying it. Pop then destroys this T2. And also this T class is nice because it shows you which instance it is and then how many in total are currently alive. So this means I'm calling a destructor of T2, which is the second T that was created, and currently there are 2 T's, or there will remain 2 T's after I'm done. Okay, so we move it off. There, and we printed it. Okay. Good. So now I want to test the case where there's a thread, and this thread is waiting, right? So the queue is empty, and the thread will be waiting. So let's see. Thread T, and we will give it we will initialize it with a lambda that will take something by reference, no arguments, and therefore I think I can skip this. So no arguments, just lambda, and then let me think. So in this lambda, all we want to do, for instance, just want to do q.pop. And once we pop it off, cout, right. And then finally, join. But this will block forever, right? Assuming let's q pop there. So now the queue is empty, and I pushed one element on it, popped one element out of it, and then started another thread. And this thread is sitting there, just waiting for something to show up on the queue. And then I'm waiting on this thread to finish. So that's fine. This is completely deadlock. Breakpoint. Okay, let's go. Yeah, so this program is going to stay running forever. So let's see. I wanted to see what we should do if this queue is being destroyed while there is a thread waiting on it, right? Because it's a case that can very well happen. So let's see. Let's move this thread out of here in a higher scope, if you would, and then in this subscope. Let's see. There, this subscope, which is going to say T equals thread, right? So what I'm doing here, I'm creating the thread object. Right now, it doesn't actually point to a thread, but it will. Then I'm creating a queue by doing some test push and pop. Then I'm starting a thread, and this thread is waiting on something to show up. But then in the meantime, I exit the scope and the queue is destroyed. And I want to see what will happen. So let's uncomment. Let's comment this out for a second. Let's put the breakpoint back here in the pop. Let's see if we'll even get there. Failed success. All right. Okay, so we did get to this pop. Well, that's because we have a thread. Yep, came from here. Okay. Let's run. There. Something bad happened. Terminating with uncaught exception. System error, mutex lock failed. Yeah, so what happened? This queue pop, right, it was waiting in this condition variable. And I suppose the condition variable's destructor maybe was caused it to unblock, where then it could try to take this lock. But by the time we got there, this mutex was already dead. So we need to deal with this case. And how to best deal with this case? I suspect you should probably handle this in the destructor. So in the destructor, it's okay to try to take the lock because if there's no one waiting, so okay, they're not holding the lock, so we're not going to deadlock. So let's do this. In the destructor, we will first take the lock. Next, what should we do? We should probably then try to clear the queue. And queue that no empty. No, can you top clear? Okay, well that's fine. So let's see. We'll do something, and then finally we will notify one again in a destructor. So if we enter this destructor and somebody is waiting, right? We want to unblock them, but how could we do that? So even if we notify, well, this guy's going to go right back to sleep because this queue at empty is going to be queue at empty is going to be false. Or queue.empty could actually be true as well. So this condition is not enough to tell this condition variable waiting whether it's time to actually lock and unlock. We need something else that would indicate whether we are being destroyed. So let's see. Let's see if we can add a Boolean here. This will be another type of a condition. Let's say let's call it M. Exit. We'll default it to false. And in the destructor, once we took the log, we will say M exit equals true. So, and then we will notify one, and we want to do it in such a way that once this condition is unblocked, then this thread can, instead of trying to take something of the queue, just exit, right? So we'll definitely need to do if an exit is true. Let's see. Return, right? But return what? And this is when things get a little hairy. We don't really want to return, create an instance of T. We shouldn't, right? So we need to change the signature of pop to maybe return a Boolean, which will tell us whether or not we succeeded or not, and then take a T, let's call it item, we'll take it back reference, so we can write into it. So then if this exit is true, pop will return false, saying, no, I didn't actually show up. I didn't actually pop anything off. It's just that we're being shut down. And here, instead of making a copy like this, item, we will move into this item, this reference here. And then we will pop. And finally, we'll just return true. So we had to change the signature of this pop in order to handle what can possibly happen during the destructor of this queue, while there's a thread trying to wait on something to show up on this queue. So now we need to change this. Okay, so we have a default constructed key, and then full result equals queue dot pop I. And let's print both the result and I. So let's first say full alpha. It will simply tell the stream that instead of printing Boolean as a 0 or 1, print it as a spell it out, print true or false. In order to do that, we need IO manip header, IO manipulators. So let's see. So in the thread that's waiting, we will wait on the pop, and then depending on what the pop returned, well, we could take a different path in this function, but we're not going to worry about it right now. Let's just see what happened. And finally, this predicate needs to change. So in what condition should we not return back to spinning here, right? Remember, this also guards against the spurious wake up. And once we're notified, that means once this wait wakes up, it reacquires the lock, but it will then check this predicate, right? And say, hey, okay, I've got the lock, you woke me up, or maybe you woke me up, maybe somebody else woke me up, but is there really some work for me to do, or should I go back to sleep? And there may be some work for it to do under two circumstances. One is that the queue is not empty, right? The other one, or we are now exiting. So M exit became true, which will then test and exit from the pop accordingly. And here in the destructor, right, we did just that. We took the log, we said, we're now actually exiting. So let's set this flag, let's notify whoever may be waiting, and so that they can exit out cleanly from the pop function. So let's see if this works. Let's see if it will still crash. Let's put this back. Right, wrong signature. Because we need an instance of the actual T to fill into, right? And it's a trade-off, right? We have this pop and we're doing it as in one go, right? It's going to pop and to pop the element of the queue and fill it into something we're passing it. So there is really no other way I can think of that we could have this signature where we're returning, right? Instead of filling into this I, it actually returns an instance of t without it needing to make or default construct this t. So let's just keep it this way for now. All right, let's see what's going to happen. We're going to push something on the queue first, then we're going to pop off of it. So this is the first time we're entering into pop, right? Because we're here on line 79. Their exit is false. That's fine. So we're not going to exit. We're going to take something. Good. So that was our first case. Now the queue is empty, and this thread will now start to try to pop. But then, because we're going to exit that scope, which is this scope, the queue's destructor will now be called. So let's see what's going to happen. Okay, so here we are. So this thread is running. So let's look at it. There's the second thread. Where is the second thread? Start. Now looks like it didn't even get that far. But it is starting. So maybe, let's retry this after we create this thread. Let's put this one to sleep just for a bit. This thread, sleep for 100 milliseconds should be enough. Let's try this again. All right, here we are, first time in the pop. Now, still, there's only one thread. Everything is good. We're here. Now we're going to start this thread. There we go. And now this thread, now we're in thread 2. And this thread started. Oh, where did this thread started? I'm going to show you the starting point. So you know which thread there. See, this is the thread word. Okay. And this guy is sitting on a pop, and this queue is empty at this point, right? Size 0. So it's going to take the log, check this this thing, this predicate here, and it's gone to sleep. But remember, when it goes to sleep, it releases the lock on this mutex. So now we're back to thread 1. Right, this is our thread 2 waiting, and this is our thread 1. We're in main, right? We're exiting the scope. So we're going to destroy the queue. And therefore, let's put another breakpoint. Yeah. So now we're on the main thread. We're going to acquire the lock. We're going now set mexit to true. Now we're going to notify. And that notify there. Now it woke up second thread, except now it sees mexit. It's true. So it popped nothing there. It popped nothing of the queue. Instead, this thread, where is it? This thread exited, and now we continue the destructor. So that unblocked. It's good. Now we can join this thread. See, this thread is now exiting. Here it prints false, right? That means it didn't actually pop anything. The result of pop is false. And if we continue running, everybody's happy and nobody crashes. Good. So let's see, let me remove all these breakpoints. Let's run it one more time, just to make sure it's not crashing because of some lucky timing. Run, good. So we had to become aware in the structure of this queue, right, that somebody may be waiting on us, and we cannot just go ahead and nuke our condition variable, nuke our mutex, right? Because that means that we are destroying ourselves while on another thread someone is actively inside one of our methods, and that's not very good. You don't want to do a demolition on an apartment building with somebody still happily renting inside. So we need to make sure that by the time we finish the Destructor, we are in fact ready to start taking down all of the objects, all the members we have, because at that point we want to know that that no other thread is actively sitting there trying to pop something off this queue. So we needed to introduce this extra variable. And notice that this predicate, right, it can test multiple conditions, not just one. And we can force it to test these conditions by notifying it if it is asleep, right? And if there's nobody waiting on this pop, well, that's fine. And this effectively a no up. Nothing is woken up. Now you may ask, well, what if there is somebody waiting, but it's destroyed on one thread, or somebody may be waiting on another. At that point, that becomes the user's problem. We need to assume and write code in such a way that we can be certain that our constructors and destructors run in isolation, right? And if they're not, it's a logic error, but it's not caused by us. It's caused by the consumer of this queue. Therefore, we shouldn't really concern ourselves with that. And finally, let's see what would be a good method to have. We have the two pushes, we have the pop. Maybe let's add a stop method. So void stop or exit or quit. I don't know. Let's just say stop. And in the stop, we're going to pretty much do what we did in this Destructor here. So we can replace this whole Destructor body with just a call stop. And in the stop, we'll take the log and we'll set this variable and notify someone if there is someone waiting. All right. So this is good there. So we have the stop function. So we can either call it explicitly, right, or it's going to be called in the Destructor. So either way, I'm going to do it. So q dot stop. We can call it here explicitly to tell this thread, to unblock itself on this pop and check the result of pop, or it will be called from the Destructor. Either way is fine. So let's run this again. Good, everybody's happy. After starting this thread, let's get rid of the sleep. Let's actually push some things on it. So Q, push, T, 2. Let's see. 2, 3, 4. There, we're gonna push some elements. There we go. And this I here, this I we will initialize with, let's say, temp. Let's try this. So we're going to push and pop. And your text log invalid argument. And again, we ran into this issue. Look at this. Thread sync abort. So a thread, this popping thread, still let's see. So what happened inside this thread? Tried to get back to this log, but it couldn't because we were destroying the queue. Now, well, let's see. See if we can debug through this. So what did we do here? Right, we started this thread. Then we push 1, 2, 3 things on it. And then we told it, hey, we're stopping. So, right. So we need to, the mistake here, we need to react from this. So if it is, so pop tells us, when pop returns false, other blocks and returns false, it means, hey, this queue is done, stop using it. So we have to stop this thread too, I think. And moreover, we should do this in a loop. So in case there's more work there. There we are. Let's try this now. Yeah, looks like everybody's happy. Yeah, because this thread, it's going to become like a worker thread on our thread pool, right? It just needs to sit there in a loop, try popping things off of this queue, and the moment it gets something, the moment it gets something like this, that tells it that we're shutting down, we're just going to stop actually working. So let's see, did it actually get to print anything? No, see, this thread didn't get to print anything because we got to the stop so quickly. So let's put the delay back in here. This thread, sleep 4, there. So now what we should see this thread actually print a few things. Where was it? R. Oh, wrong. If not R. So if we turn false, then return. Otherwise, there. It's spinning in a loop. So here, true, true, true. There. So that's good. So it popped off. It popped 3 things. Okay, that's good. Let's see. And then it went back to sleep, right? Let's remove this stop here. Try it again. Yep, everything looks good. Now, what I was wondering, after we call, and this stop, right? After we call notify 1, should we try to reacquire this lock? Because if we are able to reacquire this lock, that means for sure that whoever may have been blocked in the pop has exited from the pop. So maybe not. I'm not sure, to be honest. But we'll see. If we run into another set of crashes, then maybe the solution to it will be to notify this and then try to reacquire this lock. Okay. So this is an unbounded multi-threaded producer consumer queue. The producer can keep pushing things on it for as long as it wants. It will grow indefinitely, right? So maybe now let's get back to our thread pool and see if we can rework it. Let's take this main. We save the copy of this main for later. And let's see if we can now go back to our thread pool class and simplify it. So simplify it by using this unbounded queue. So now this thread pool should no longer even need a condition variable and a lock, anything like that, right? Because all of this locking and unlocking will be now taken care of by this queue. So let's see. So work item, no need for that. Let's see. Do work. Okay. Let's also try to change it to to not use these unique pointers anymore. Okay. So we will only need a vector of threads, right? No queue. Queue is no longer our member that we really have to manage. So let's just now use the queue we just implemented. So we're going to have some threads, and we're going to have the queue. This time it's going to be queue unbounded queue of. What is this queue going to be of? It's going to be a queue of work items. There. So let's actually let's create an alias for that. So we're using qt equals this, and then qt queue. There. Now let's see. Work queue. This we don't need. Work item pointer. This we also do not need. Good. So this thread pool now should become simple or simpler. Okay, so let's do work first. So when we do work, we don't need to take any locks. We just say, hey, queue, go ahead and push. So that's it. It's a pretty simple do work because it will already do all the blocking for us and locking and all of that. And then the destructor. Here's the nice thing. The destructor, let's see, it still needs to, it doesn't need to take any locks anymore. All the destructor has to do, let's see, there. Destructors needs to push the sentinels, right? But let's move this work item. Maybe I need to. Yeah, so for every thread, we just want to push work item T. Right, just want to push an empty work item. Again, because this STD function can be in a state that's empty, and we can test for that. So this was WI. Okay, yeah, we're gonna move it in here. The destructor becomes simpler. We're just pushing. We're pushing as many sentinels as we have threads. That's good. Now let's see. The actual worker threads. Work item. Oops, our work item. There. Work item pointer. We don't have a work item pointer. We just have a work item. Here, empty one. Again, no need to do any of that. So all we got to do now is mq pop work. If no work, then break. And if work, well then let's just do work. Let's see if this is going to work. Yeah, well, pop, check it. I think this is the right type of check on STD function. Maybe let's see. Work dot. What do we have here? Function. There, operator boolean. That's it. Yeah, it looks like this check here is correct. Okay, let's build this. See if this builds. Woohoo! Good. Let me just look this over. So Q. Thread. See how nicely we were able to simplify the thread pool. It just creates those worker threads, and they become really, really simple, right? Just pop the next item off of the queue. If it's got no work, exit. If it's got work, yay, just do it. And then do work. Again, we've shifted all the responsibility for managing this resource, this queue, away from ourselves and onto that queue class. So let's see. Let's build this. We'll run it from a console. Here we are. Very nice. Still works. So let's take this unbounded queue, make a copy of it. Let's say here. Let's make some spaces here. So let's also rename this thread pool. So we create an unbounded queue. So we're going to have an unbounded thread pool. Let's get it out here. And I will eventually clean it up. So let's call it unbounded thread pool. Yeah, let's call this unbounded queue. There. This is this. Good. Now the thread. The thread will now use unbounded queue. Good. Item. Yep. Unbounded thread pool. Just rename those things here real quick. And let's see, we didn't need to define any other special members for this queue because of this mutex condition variables, non-copyability or movability. You can also get rid of this, simplify it even further. Because it's just going to fall back on whatever it holds, and if the members do not allow it, therefore this pool class will not be copyable or movable either. Okay, unbounded thread pool. Let's see if we're still good. Still building. All right, everything looks good. So let's now create a bounded queue with a maximum capacity. Here we are. Let's take a copy of this. Okay, so now we're working on a bounded queue. Here, everything else looks fine. Okay, and now we need to specify what's the maximum size, right? std size t. Size t is pretty good for that, since it's unsigned. So no -1s or anything will come through here. Let's call it what? S for size. We're gonna have to store this variable somewhere. So we'll do m size s, and I think that's it for now. Size member, right? We don't have this member, of course, but we will. M size, and it should probably be something like m max size, right? Because that's the maximum size, not the current size. So let's not confuse the two. Okay, so m max size. Yeah, that's fine. So all of this looks good. Now what we want to do these checks in push, right? We only want to push if we have not yet reached the maximum size. So let's see. So first of all, think about how we would test this. Let's comment this out again. Let's recreate our test. See if I can just cut it and then paste it again to get, there we go, okay, looks better. So here, now we will use bounded queue. No much constructor, that's right. What size do we want to give it? Let's just give it 1, see what happens. We definitely want to react if we give it 0, so let's do that real quick. Bounded queue, if s, let's see, bed queue size, bed queue max size. It's been on 0, of course. All right. So let's do this. We're going to create this queue with size of 1. That's fine. Let's not worry about this. So we will have this thread still going on here, and this thread will just spin in a loop, trying to pop things. So nothing really has to change here. I'm just going to try to pop it and print it. But then the trick will be, let's see, for 1, let's push 10 things onto this queue, but do it with some sort of a delay, right? So we will push, and then we will sleep. Let's here. And of course, somebody's got to increment this line. There, so we're going to fire off this thread, and this thread is going to sit in a queue, and it is going to pop, and this thread, the main thread, will push and then wait, right? And we will test the max size of this queue, because later we will remove this wait, right? And we will instead put it here to kind of keep this guy from being able to push too much. So at any given time, let's also Let's add some helper methods to these queues. So stop. Let's add maybe something like size and empty. Gonna be helpful, I think. So std size t size. That is just going to return MQ, that's size. Now should we take a log? Possibly. So let's take a log before we test its size. And similarly, empty. And this will not compile now. You'll see why in a second, because of these methods being constant. And trying to acquire a log modifies a member. So we'll have to make the mutex a mutable member. But anyway, let's take the log again, return MQ dot empty. So these are maybe good useful helper methods for later. And now if I try to build it, let's see. Assuming everything else is good. It succeeded. Interesting. That's probably because I didn't even call them. Or no, wait, I'm using it in a unbounded queue. So let's copy these methods, size and empty, into our bounded queue. Try to build this. That should fail. No? Or is it because we're not calling it? So fine. Let's call it cout queue dot size. That should fail. There we go. Okay, see now it's failing. Because we are trying to modify. Yeah. So remember, let's type non-const, so on and so forth. So back to the queues. And we need to, or is it? We need to mark this mutex as mutable so that it can be modified inside constant member functions. And the same thing with bounded queue. There. Let's try this now. Good. Now everybody's happy. So we build this. When we run it, okay, well, it's printing a lot because of all these, right? Yeah, because of all these traces from T. So maybe instead of doing the bounded queue of this T, let's just do it of int. For now, size 1. I, okay, and then push. Yeah, just let's try this again. Okay. So you will see it's printing 1, 2, 3, 4, 5, and so on, and then in between it prints zeros, right? Because the queue. This thread was sleeping, so it's not a bounded queue yet, but this thread didn't have the time to push more. So let's instead push this sleep here. So now it should start with the queue size probably 9, and then nope. Oh. Oh, that's nice. Let's see what happened. Started from inside here. So we blew up on time. Turning. Bounded queue pop. Okay. And which thread? Which thread blew up? This one. Right. Yeah, because we're not, okay, so we're not, no, we're joining on this thread, but too late. So what happened, right, I pushed all these elements, then I told it to stop, and then I exited the scope. And then, because of this sleep, the this thread woke up and then tried to go around back to the queue and pop something. But at this point, the queue has already been destroyed. So, okay, but we know our destructor works like it's supposed to, so let's just remove this scope here. We don't need it. So we can keep testing the rest of the code without worrying about those cases. Thread T. There. Now it should be fine. Success. Stop. Right. Let's remove the stop. So this thread didn't have a chance to print anything. There. Okay. Let's actually put some better tracing. So we are printing value is this, and then we'll just print the size right afterwards. Say this size is there. Keep that size. Should look more friendly. There. See, so we popped something and then we print the size, so it makes sense, right? 987.654.810. So that's good because we pushed onto this queue as quickly as possible, but then we were popping off this queue slowly. So nothing, this parameter, this size, this maximum size of the queue didn't stop this thread, the main thread, from pushing more and more work onto this queue. So that's not good. That's what we want to implement, right? Let's see. Yeah, this thread kept on running. I just noticed it got stuck because, well, because we're not destroying this queue. So it's sitting here waiting on a pop, and we're sitting here on the join, and this queue is still alive. So because we have the sleep here, let's put another sleep after we push everything. There, so let's wait. Let's give this guy 1 second. Let's give this guy maybe just 10. And after this sleeps for a second, we'll do queue.stop. So we can then cleanly exit from this worker. And let's just move this variable inside the loop. And I say move it inside the loop. Because it's an integer, it doesn't matter here. But if it was something more complex, right? After popping it and storing in this variable, and then doing another round through this loop, that I would still exist. So this could potentially be a leak of sorts. But by putting it in this inner scope, after you pop it off the queue and you're done using it, and you make another round into through this loop, you have then destroyed this local I. So let's see. Now we added a second, added stop, join. So now this this program should exit cleanly without being blocked. And there we go. So how would we implement this bounded queue, right? We're telling it we want some max size. So we have this max size somewhere. And then we have the current size of the queue, of course. So let's see. Let's go to the push. And let's just implement. Well, never mind. So we want to go past this push only if the size has not reached max size. So we can wait on the condition. Let's see, we probably need a second condition, I think. Right, because now the thread can be blocked on a push, right? Just like the popping thread can be blocked on the pop on this condition here, right? And only be woken up after a push. So this push now should also wait on some sort of a condition and only be woken up after a pop, right? So once it successfully popped something, it should then say, hey, pushing thread, you can go ahead and push some more because I have just freed up some room for you. But can we reuse the same condition variable? Likely not, right? Because there may be other threads waiting on it. So let's add another condition variable. Let's rename it. So first condition variable, we'll call it condition push. The other condition pop. So condition pop, we will use wait on it in the pop, and we will notify it in the push. Condition pop. There we go. And then in a stop and in a destructor, we likely want to notify these pushes also. So let's see, condition push, notify one. Where else? Okay, that's it for now. Good. Okay, so push. Let's do this. We still have to acquire this lock, right? So we don't need another lock because all we're really guarding here with this lock is this queue. That's what we're always guarding. So we do not need a second lock, I do not think. But we certainly now need two condition variables. So we did condition variable pop. So let's try to do this. In a push, we'll take this lock, and then we'll wait on this condition and what will be the condition? We want to unblock, so return MQ size. So if this predicate returns true, then we can happily unblock. Okay. So we want to unblock when size of the queue is less than M max size. Right? Makes sense, I think. So, and remember this, did I spell it? guard. Yeah, guard. Yeah, so we're going to take this log and then check, can we actually push something? So is this queue already full or not? So we're going to check this, we're going to run this predicate, and it's going to tell us, okay, queue that size. If it's less than max size, perfect, we can push something. Otherwise, back to sleep. So this is first push. Let's now do the same thing in the second push. Okay. And after we pushed, we notify the pop condition. And in a pop, after we popped something off, we need to now notify the push condition, right? So in case the push was blocked on another thread, waiting for some room, for more room to show up, well, once we pop something off of it, we can then notify it there. However, we're missing one thing in the pushes, right? Because the push can be blocked on another thread. In the meantime, we call this bounded queue.stop, right? So we want to unblock this thread. So we need to check for the same condition here. So or exit, right? So we want to unblock this wait in a push if we have some room or if we're exiting, right? And again, if exit return, suppose we could return false, so change the signature of push. Okay, and if we successfully push something, return true. Same here. Return true. And let's add this condition here as well. So or, right? So unblock, stop sleeping if we have room, or if we're exiting, if exit, return false. There, return false. So now, assuming it's built, there we go. So now what's going to happen is we're going to tell this queue, hey, your max size is 1, okay? So after there's something on this queue, you cannot push anymore. So that this should block this push until this popping thread takes something off, and then it allows for another push to take place. Okay? And after we pop, right, so in a pop, once we made some room, we notify this second condition that, hey, there is room now, so in case there is a thread waiting on a push, it can now be unblocked, and it can check that, okay, now there's some room on the queue. So this, and another mistake I just realized, in this queue and the other queues, when we're doing a stop, we don't want to notify one, we want to notify all. There, because there may be multiple threads waiting, blocked, and we want to let all of them know that we're stopping, not just one. And same here. Notify all waiting threads. There. So if this works, which I hope it does, what we should see is this thread that's popping off, it's going to print the size, and it should never get to a point where it's showing size greater than 1. There. It even printed size 0, which is fine. Means it popped something and it did it faster before this thread now got unblocked. Let's see, let's increase this weight here a little bit. So let's give this 100 milliseconds so we can see this. Happening. So this is gonna push. So every time we push, let's print something. Hopefully it won't get all interleaved with what Pop is printing. Yeah, it kind of did. Okay, never mind. But let's now increase the size, the maximum size of this queue. Let's say, let's make it 5. And let's maybe push some more on it. No, sure, let's do a 50. Sleep, decrease the sleep a bit. I will run it from the console. And we will see there, as this is going, see the size of the queue never exceeds our maximum size. It's sometimes 1 less, but that's because those threads are competing for this queue, right? But they never exceed. So now we have created a bounded multi-threaded queue. So this can throttle the producer, right? This will eventually go in and stop this producer thread from pushing too much onto this queue. Let's see. Let's try 15. See how that's going to work. There. See, so initially they all get, the producer gets to fill up the queue, right? And when the producer stops, then it starts dropping. Size of the queue decreases until it goes to 0. And again, these 14s are okay. That's simply because these threads are competing for this resource. And sometimes we get to print this value before the main thread gets to push something onto this queue. So yeah, this is, I'm not gonna show you how to now wire this into the thread pool, because that's easy. You would just need to add a parameter, extra parameter to the unbounded thread pool. And in fact, yeah, let's keep it unbounded. Maybe no, maybe let's just keep it this, and we can make whatever type of a queue it's using. We can make it a template parameter to this thread pool. And I would then need to, just replace it here. Okay, yeah, you would add an extra parameter to the thread pool, not only the thread count, but also the maximum size of the queue. You obviously would want to make it bigger than the thread count, right? Otherwise, it would be kind of pointless to have 10 worker threads while only being able to keep 5 items, push 5 items in the queue. And this way, if you run into situations where your producers are producing too fast and the thread pool can consume, then you could throttle it. So this blocking queue, I had that implementation from a few years ago. I think it's still up on my blog. I actually implemented it using semaphores. It was easier to reason about it in terms of semaphores. I had 2 semaphores and a lock, and the semaphore one would be counting the empty spots in the on the queue, and the other one would do the opposite. So one semaphore, if you had max size, one semaphore would be counting from 0 up to max size, and the other one would start at max size and then counting down to 0. And using the semaphores, I was able to notify the producer and the consumer that there's room or that there's an element on a queue. So just like our pop and push are waiting on one condition and notifying the other, see, push waits on the push condition and notifies the pop, and pop waits on the pop condition and notifies the push. So instead of being wait and notify, it was just semaphore post and semaphore wait, right? So increase increase the count of the semaphore, and then another thread would wait on it, right? And semaphores will go through the wait without blocking until the semaphore count drops to 0. So if you had a semaphore that counted how many empty spots there are, right? Once it dropped to 0, that means you've reached your maximum capacity. And another semaphore that would count the opposite of that, which is how many elements there are on the queue. So every time you would pop off the queue, you would drop the count of that by 1. And once you reached the count of 0, you knew that, well, there's nothing on the queue for me to pop. There's nothing for me to do, so I just need to block. Let's see. Yeah, it's good to know that these predicates, right, for condition variable, they can check whatever. It can be looking at multiple conditions, and we had to add this exit flag to keep those threads that we're trying to get work off of these queues from crashing, right? From then trying to access this queue after it was already destroyed. Let me look this over one final time. Queue, bounded, good. Thread pool, unbounded. Okay. Let's run the thread pool test one more time. So we are going to thread pool. Do some work on it. It's good. And then we're going to test the bounded queue. So this doing work that's coming from the thread, right? It was sleeping here for a while. Okay, I think that's it for today.